So, let's talk about encryption and decryption. You know, it's like locking your house but with math. The key is the combination to open that lock.
I get that part, but how does it work with digital data?
Well, you start by selecting an algorithm, like ICE or RSA. Then you apply a key to transform plain text into ciphertext. It's like mixing paint colors to make a new color. Only the right mix can recreate the original.
That sounds complex. How do we ensure the keys stay secure?
Oh, that's the tricky part. You need to manage them carefully. Use secure channels for transmission, and maybe even encrypt those keys again using another layer of encryption. Think of it as putting your precious items in a safe, within a safe.
What happens if someone gets hold of both the encrypted message and the key?
They'd have quite a challenge on their hands, depending on how strong the algorithm is. A brute force attack would take years with current computing power, especially with something like 256-bit AES. But yeah, security through obscurity isn't enough. Robust algorithms are crucial.
Makes sense, but what about quantum computers? Don't they change everything?
Quantum computers could potentially crack some classical encryption methods much faster than traditional ones. That's why there's research into post-quantum cryptography, algorithms designed to resist quantum attacks. We're not there yet, though. It's still largely theoretical at this point. Speaking of algorithms, let's touch on symmetric versus asymmetric cryptography. Symmetric is simpler. Same key for encryption and decryption.
Right, so it's like having a single key that locks and unlocks the door.
Exactly. And it's generally faster too. But managing those keys can be a hassle, especially when you need to securely share them between parties.
That makes sense. What about asymmetric then?
Asymmetric uses a pair of keys, a public key for encryption, and a private key for decryption. It's more complex but provides better security, because you don't have to worry about sharing the private key over insecure channels.
So, it's like having two different keys, one to lock the door, and another to unlock it.
Precisely. This setup is great for scenarios where secure key exchange is difficult, like sending encrypted emails or securing web traffic with SLS/TLS certificates.
That seems safer, but wouldn't it be slower, compared to symmetric?
Indeed, it is typically slower due to the complexity of the mathematical operations involved. That's why often both types are used together, like in hybrid cryptosystems where data is encrypted with a fast symmetric algorithm, and the symmetric key itself is encrypted with an asymmetric algorithm for secure transmission.
Ah, got it. Combining both gives us the best of both worlds.
Absolutely. Each has its strengths and weaknesses. Knowing which one to use in different situations is crucial for effective cryptographic practices. Another important concept is hash functions. They take input data of any size and produce a fixed size output called a hash value or digest.
So, it's like squishing all kinds of information into a small, consistent package.
Exactly. Hash functions are deterministic, meaning the same input always produces the same output. They're also designed to be irreversible. You can't easily figure out the original input from the hash value.
That sounds useful for verifying data integrity without revealing the actual content.
Precisely. One common application is in password storage. Instead of storing passwords directly, systems store their hash values. When a user logs in, the system hashes the entered password and checks if it matches the stored hash.
Makes sense. What about other applications?
Hash functions are also used in digital signatures to ensure that messages haven't been tampered with during transmission. In blockchain technology, they help create a secure chain of blocks by linking each block to its predecessor through unique hash values.
That's fascinating. How do collisions affect their reliability?
Good question. A collision occurs when two different inputs produce the same hash output. While theoretically possible, good hash functions are designed to minimize this risk. For example, SHA-256 produces a 256-bit hash, making collisions extremely unlikely under normal circumstances.
So, choosing a reliable hash function is crucial for maintaining security and integrity.
Definitely. The choice depends on the specific needs of the application, considering factors like speed, security level required, and resistance to various types of attacks. Speaking of security, let's talk about key management and distribution challenges. Ensuring that keys remain secure throughout their life cycle is crucial but also quite complex.
Absolutely. Now, it feels like a logistical nightmare to keep track of all these keys, especially in larger systems.
Indeed, one major challenge is securely distributing the keys to all the necessary parties without interception. If an unauthorized party gets access to the key, it can compromise the entire system.
That makes sense. Are there standard protocols or methods for handling this?
There sure are. Key distribution centers, KDCS, and public key infrastructure, PKI, are commonly used. KDCS act as trusted third parties that facilitate secure key exchanges between entities. PKI uses digital certificates issued by trusted certificate authorities, TSESS, to manage public keys.
How do you handle key expiration and rotation then?
Good question. Regularly rotating keys is essential to mitigate risks. Automated tools can help with this process, ensuring that old keys are retired and new ones are distributed securely. It's also important to have clear policies on when and how often keys should be rotated, based on the sensitivity of the data they protect.
That sounds like a lot to manage. Any tips for simplifying this process?
Definitely. Using centralized key management systems can simplify things significantly. These systems provide a single interface for generating, storing, and distributing keys across different applications and environments. Automation features can also reduce manual errors and free up time for more strategic tasks.
Centralized management does sound easier to handle.
Absolutely. And don't forget about physical security measures for storing hardware-based encryption keys, such as ASMS, hardware security modules. These devices provide additional layers of protection against theft and tampering.
Physical security is definitely something to consider too.
Exactly. Balancing ease of use with robust security is key here. Getting it right ensures that your cryptographic practices are both effective and manageable in real-world scenarios.